In this demonstration, we're going to look at molecular shapes. Specifically, we're going to look at molecular shapes in terms of what's called the valence shell electron pair repulsion theory, or VSEPR. Although the VSEPR theory is very simplified, it's a very powerful tool to let you know how other atoms and electron groups are arranged around a central atom. Now, one way to illustrate this, to look at this, is to remember that electron groups around a central atom will try to get as far apart from each other as they possibly can, whether they are bonding electron groups or non-bonding electron groups. Non-bonding electron groups being a little bit larger. One way to illustrate this is with some balloons. So I'm going to look at two electron groups, or electron domains they're sometimes called, around a central atom. If I have these on strings and I draw them as close to each other as I can, the natural shape that they take is in a straight line, like so. All right? They don't like to be at an angle or anything like that. They like to be at 180 degrees to each other. That can be represented in a molecular model kit like so, regardless of whether I have little balls on the end of these or just straight links. It represents the electron groups, whether they're bonding or non-bonding, to be 180 degrees apart. That's illustrated in this model that we have right here, 180 degrees apart. Using the balloons again, and we want them to be of similar size. If I add a third one to the group here and try to pull it as tight as we can, we see that the natural shape that they get to get as far away from each other as they possibly can is in a triangle shape, or what's often referred to as triangular planar. Here, we're looking at a model where they're in the same plane and they form a triangle, and here as well. Now for the balloons, as we add more, it gets a little bit more difficult to do with my hands here, but I'll do the best we can. When I add this one, it pushes that triangle down a little bit, and it forms an object that we call a tetrahedron. It's basically got four equivalent triangular sides, and this is a tetrahedron that we have right here, and this is another tetrahedron right here with just a different model kit. Again, it's going to get more difficult as we add some, but I'm going to try to add a fifth one and see what I can do. It's hard because I can't get my hand out of the way very well, but I'll try to explain a little bit of what it looks like here. Now we've got a triangle of balloons in the middle, and then one on the top, one on the bottom here, which looks on a molecular model kit like this one here. The two on the top and the bottom directly apart from each other, and then the three in the middle on the same plane. Right? So this is called trigonal bipyramidal, triangle in the middle, and then kind of forming two pyramids, top and bottom. Lastly, I'll try to add one more. This gets, again, a little bit more difficult to do. The more balloons that we have, and it's going to be somewhat difficult to visualize here, but what we're forming here, and it's harder to see, is what's called an octahedron, which is this shape right here, where the shape in the middle is a square, and then we've got two coming out straight from each other, and it forms an eight triangular sides, which is what we refer to as an octahedron. So again, the main purpose of this demonstration is to show you that molecular shape is determined around a central atom by how far apart the electron domains, whether they be non-bonding electron pairs or bonding electron pairs, how far apart they can get from each other to minimize the repulsion. And again, this is what is known as valence shell electron pair repulsion theory, a very important theory in explaining, a simple theory explaining molecular shapes. And in chemistry, it's very often the shape of the molecule that determines the function.